Hello, this is Timberlake Basic Chemistry. We're in Chapter 9, Chemical Quantities and Reactions. And this is the 9.1, the mole relationships in chemical equations. If you have a chemical equation, that means you have something equal. And what you have equal is amounts. You have amounts of stuff at the beginning and amounts of those same elements at the end. The elements can break apart, so compounds can break apart and reassemble in different configurations, but you're going to have the same amounts. So if you're given weights, like so many grams of this and so many grams, that's what you're going to use if you're going to measure something, because I don't know how to count molecules, but I can measure them on a piece of paper on my scales. But weights is not a number. Weight has to do with how big something is or how massive it is or how heavy it is. And so I need to know numbers. Once I have a number, then I can go from one equality on the left to the equality on the right, and I can know what's happened. So your rule of thumb always is go to moles. Convert from grams to moles. Then do relationships in the balanced equation. Once you know what's going on, if you want to know something, if you want to know how many grams something is, then take the moles that you have and go back to grams. So you are using the molar mass from the periodic table to go from grams into moles, then deal in the equation, because it's numbers to numbers, it's a ratio, 2 to 1, 3 to 6, whatever, then go back to masses if you need to. So that's the rule of thumb. Law of conservation of mass: you don't make stuff by doing a chemical reaction. You do not create matter out of thin air simply by burning something in air. You don't get rid of anything and you don't add anything. All that you do is reconfigure. Legos break apart, Legos join together. All right, so that's what you need to know. The law of conservation of mass simply means that the same amount of mass at the beginning of a reaction is exactly the same amount of mass at the end. Same number of atoms at the beginning, same number of atoms at the end. So if you take configurations of Legos, weigh all of the Legos you're going to play with before, then take them all apart and put them in different configurations, and then weigh them all again, you're going to get the same weight. And that's exactly what's happening here. This is called the law of conservation. So if you were to have sulfur, okay, in this case 32 grams of sulfur, and 215 grams of silver, and you make it into silver sulfide, once it's a new compound, all of that silver was used, all of that sulfur was used, it's still there. You're simply adding up the masses. So the mass of one plus the mass of the other equals the mass of the resultant. The problem is I want relationships. I want to say it goes from it was combined 2 oxygens to one at the beginning, and now it's 3 to 2 at the end, or whatever the balanced equation was. Those are in moles. I want to go to moles. So even though that the grams are all conserved, I want to convert those grams into moles, because that's a number, and I can do a ratio with a number. Okay, and it's ratios that I'm looking for. Is it 2 to 1? Is it 4 to 5? Whatever. That's what we're looking for. But this is true. Whatever the mass of the stuff is at the beginning is exactly the same mass at the end, but it's new stuff. Okay? Silver sulfide has different properties than silver does and different properties than sulfur does. Okay, so here we've got iron and sulfur making iron sulfide. So when I look at this, I immediately think 2 atoms of iron and 3 atoms of sulfur give you 1 molecule of iron 3 sulfide. That's what I'm thinking. Or 2 moles of iron and 3 moles of sulfur equals 1 mole of iron 3 sulfide. Okay, so an equation can be read in moles by placing the word moles of in front of the coefficient. 2 moles of iron, 3 moles of sulfur. Remember, it's a 2 to 3 relationship. Iron and sulfur combine in a 2 to 3, always. So 2 atoms to 3 atoms, or 2 truckloads to 3 truckloads, or 2 whatever bathtubs full to 3 bathtubs full, or 2 moles to 3 moles. Okay, so I'm always thinking in moles. So a mole to mole factor is the ratio between 1 to the next. So how does iron combine with sulfur? 2 to 3. Okay, so 2 moles of iron react with 3 moles of sulfur. For every 2 of one, you've got 3 of the other. Okay, how does iron relate to iron sulfide? For every 2 iron, you have 1 iron sulfide. Okay, how does sulfur relate to iron sulfide? For every 3 sulfur, you have 1 iron sulfide. That's the relationship. So for that reason, you can make ratios of equality. Okay, 3 on one side equals 2 on the other one, or 3 equals 1. Because of that, you can make if you remember, making these ratios is simply taking 2 equal things and dividing it by itself, which is just the number 1. And when you multiply with the number 1, you're not changing value, you're just changing in case of moles of one into moles of another. So I can look at a balanced equation and say, if I know it's 2 to 3 and I have 20 moles of one, I'll have 30 moles of the other. It's a relationship based upon ratio. And that's why you can get everything from the balanced equation. So here's an example. 3 hydrogen atoms, 1 nitrogen atom yields 2 ammonia molecules. Okay, so here we've got 3 to 1, or 3 to 2, or 1 to 2. Okay, all those relationships. So if you know how much nitrogen you've got and you're asked how much ammonia you will get, it's a 2 to 3. And so you can use the ratios in order to figure them out. So they're saying, what is the mole ratio for hydrogen and nitrogen? Well, hydrogen is 3, nitrogen is 1. So it's 3 of hydrogen, okay, in 1 of nitrogen, okay? So it's this. Or it's the flip. Remember, 3 moles hydrogen, 1 mole nitrogen. It doesn't matter which way it is, 1 over 3 or 3 over 1. It's exactly the same because they're equalities. B part of mole factor for ammonia and hydrogen is, okay, well, for every 1 of nitrogen, I've got 2 of ammonia. So I'm looking for 2 moles of ammonia and 1 mole, 1 mole of hydrogen. So here it is right there. That's the relationship that you're going to be using as you go from one to another. So tomorrow we're going to play with all this. Lastly, how many moles of iron are needed for the reaction of 12 moles of oxygen? Okay, so here's where we're going to use the ratio. I am going to say I have 12 moles of O2. And it's a 3 to 4 relationship. Okay, so 3 is to 4 as 12 is to what? Okay, now do you see? I've got 12 is to something in the same way that 3 is to 4. Now I went both right to left in this case. I can do this 3 or 4 different ways. Knowing that I've got 12, I could say 12 is to 3 as x is to 4. Okay. Do you see? I could have done it that way. 12 moles of oxygen is to 3 moles of oxygen as what moles of iron is to 4? You're going to get the same answer either way because they're all configured in the same way. I could say 12 over x equals 3 over 4. Okay, that's what I did over here. Now, how do I solve for x? Well, I've got 12 times 4, okay, is 48 equals 3x. 3x equals 48. Okay, well, 3 into 48 is 16. So x equals 16. It's 16 moles of iron. All right, so I know that's just the first time you've seen it, but that's how you begin. Okay, so try to watch this as much as it can to get this in your head so that you can move to the next step because we'll be doing some new stuff tomorrow. All right, see you tomorrow.